this session is Vadim Smelyanskiy, who will tell us about quantum annealing via environment-mediated quantum diffusion.
Thank you. And I would like to thank organizers, and including myself, for and co-authors on that talk include Davide Venturelli, Alejandra, and Sergey Knush from NASA, and Mark Dickman from Michigan State University. And what we like to do is to describe a very simple problem with some conclusions which were not expected. This problem is not meant to be immediately generalizable. However, the conclusions perhaps will be. What we would like to do is to start with the Kimbo-Zurich mechanism in quantum annealing, something that Anatoly Polkovnikov, I think, made it available to quantum annealing community in 2005. And it really is a simple thing. If you have a system with a quantum critical point, and then you drive the system through that point varying a parameter, for example, transverse field, if you're talking a linear chain of spins. And what happens, the energy gap separating the ground state from excited states in a limit of an infinite system size go through the singular behavior. And this is a typical example. And just leaving all the details completely out of this talk, I just wanted to say what is important, then this delta, this energy gap, is some function of a difference between the value of g, this parameter that you're using, and a critical value with some exponents, which are called critical exponents. And at the same time, as you get closer and closer to the phase transition, your correlation length grows. So there is several exponents explaining how this correlation length grows as a function to the closeness to the transition and how the gap shrinks down. Now, what is important, however, that there is another parameter, another feature in that dynamics that plays a role. Because as you get closer to the critical point and your gap shrinks down, at some point, if you move with the constant rate, the rate how the gap shrinks down, you no longer be able to support adiabatic behavior. And the condition for that is really very simple. A logarithmical derivative of the gap as a function of time needs to be comparable to the gap itself. That's a condition where the adiabaticity breaks down. Well, if you have that condition, and if you assume that your transverse field is changing linearly, your parameter is changing linearly in time, and you have relations between the gap and correlation lengths and transverse field through the critical exponents. You can solve these equations. And the end result of that solution would be that you can determine the point where the adiabaticity breaks down. And the point for a given rate with which you pass through the critical point. So at that point where the adiabaticity breaks down, you can compute the correlation length, or people say density of defects. In the quantum annealing, you can compute number of excitations that you still left with by the time the adiabaticity broke down. And that number of excitations can be connected to the rate with which you pass through the critical point and some critical exponents that meant to be universal. The net result of that analysis, specifically for example, linear chain of spins in a transverse field, Ising spins in transverse field, is very simple and recognizable. All critical exponents are equal 1 in this case, and then you have one simple result. As you pass through the critical point, the number of defects that you have scales as a square root of the velocity with which you move. And this is a very simple correspondence with the law that we already know, that the time that it takes for adiabatic evolution scales as the inverse of the gap. Those two things are connected with each other. However, in this talk, we will not be interested in finding a ground state of any system. We will be interested in that paradigm. As we are moving with some velocity, we are going through the bottleneck, and we are interested what is the approximate solution that we are left with after we pass through that critical region or something like that. So in that regime, this behavior n proportional square root of v it's a very good starting point. What we like to do today is to describe an extremely simple example. However, again, it's a linear chain. It's an Ising chain of spins in a transverse field with no disorder. What we like to do, however, we would like to examine how that simple prescription given by the Kimbo-Zurich mechanism is changing when you add coupling to environment. What we're going to do, we're going to add coupling to environment through the spin flip process, essentially coupling to sigma x. At every spin, sigma x Pauli matrix will be coupled to its own Beth, thermal Beth, through the operator xj. And it's a thermal Beth, you can call them bosons. We'll consider bosonic Beth. Now, what is important, that process corresponds to a simple classical spin flip process in a Glauber dynamic. That's a counterpart. Now, what is important also, that closer to the end of quantum annealing, when the transverse field is relatively small and Z bases become essentially more native bases for evolution, whatever sigma Z noise loses its significance in terms of making transitions between the state. However, sigma X survives. So that noise becomes important, as we're going to show later, exactly in the range of quantum annealing, where something interesting can happen if you have that noise. So just to set up the stage, I would like to say that the linear chain I just described could be described in terms of the free fermion gas. It's a non-interacting fermions in the absence of coupling to environment. Once you add environment, they can, of course, start interacting to each other. But what, in the absence of coupling to environments as a free fermion gas, what I can do, I can enumerate every fermion with the momentum after doing certain transformations, Wigner-Jordan, etc. Every fermion has a momentum k, and k varies from a negative to positive value with a very small step inversely proportional to the number of spins. And then I can write down the Hamiltonian, and there is an energy for each fermion. In fact, what we plotted here are energies of fermions with different k, with 2 fermion, 4 fermion, 6 fermion, etc., described by different colors. So every fermion goes through the minimum gap with its own. The gap determines its own value, determined by the value of k, by its own momentum. So that's a kind of a dynamics. The whole system is essentially represented by the independent fermions, and every fermion has its own minimum gap. That's a system. And what is important here is that typically that dynamics is described by these Bogoliubov angles that essentially determine the overlap between this pair of fermion states and the states with no fermions in each sector of its own momentum. That sounds complicated, but there are really 2 questions which we could ask for that kind of quantum annealing. There are 2 strategies. One of them, what if we try to stay in a ground state and try to move as fast as possible? Maybe in this case, we can move so fast that we will be able to avoid problems with dissipation, because dissipation takes finite time. And on the other hand, maybe we don't have to do it. Instead, we move slow enough, and we let the dissipation to build an instantaneous equilibrium distribution in a current Hamiltonian. And maybe as we do that, we will be able at the end to bring the system to the ground state, because the gap becomes large and the temperature is not changing. So there's 2 different strategies. What we would like to do is to examine the first one. Can you actually get a meaningful speed up if you just try to move as fast as possible, but of course being fast have certain limitations to it? Because if you move extremely fast, your Landau-Zinner mechanism will generate U defects, as we talked with the Kimbo-Zurich mechanism, right? That's what the origin is. However, if you move too slow, then thermal excitations will get excited. And in this approach, what we are really doing, we are moving just fast enough to create a sweet spot, right? We minimize both quantities at the same time. And in fact, you can convince yourself that there is the total probability to be in a ground state at the end in certain regime is 1 minus probability to get excited through the Landau-Zinner with all these fermions to get excited, and the total probability of excitation coming from the ground state due to the thermal bath. And again, there is a regime when you move just fast enough so that simple approach actually is accurate one. Then all you need to do just to include the probability of excitation up without worrying about going down. Well, if you carefully compute Landau-Zinner transitions and the total probability of excitations as you go through the critical point, you have the probability to be in a ground state is inversely is exponent to the minus n. N is a number of spins that has two terms in it. One of these terms corresponds to non-adiabatic Landau-Zinner transitions and recognizably is proportional to the square root of the velocity with which you move. Another term, again an exponent, is inversely proportional to the rate with which you move. That corresponds to the effects of noise and excitation, environment, I should say, excitation from the ground state. Those two dependencies on velocity goes in opposite direction, so you can optimize this. And if you optimize, you actually get some answer. And you get the answer that exponentially depends on the number of spins, but it does have a temperature to this power 4/3. So what does it tell us? It's in this yellow box. And essentially it says the following, that for the temperature that are still larger than the minimum gap, please note that the gap is 1/n. So if I have a temperature that are still, in fact, much larger than the minimum gap, that means that I allow excitations to occur. It is possible to achieve the level of performance of adiabatic evolution without noise. So you're moving with sufficiently high temperature, but you're moving fast enough. And that is the conclusion. Well, that conclusion is not particularly scalable because you need your temperature to scale smaller than 1/n to the power 3/4. That rarely happens. Maybe in some range of n it's possible, but that's a conclusion. What we like now to do is to consider a different approach. What happens if we actually move sufficiently slow? But again, I want to emphasize, we are never going to move with any velocity that scales inversely to the system size. We're going to move with a constant velocity now, with velocity that does not depend on the system size. And we would like to ask, can we move with that velocity and still maintain a quasi-equilibrium distribution, perhaps, or whatever we get at the end, and still find a solution or approximate solution with some accuracy? So to do that, we write down the spin-boson interaction, and again in this picture with momentums, those PQ are fermion operators corresponding to momentum Q, and XQ are corresponding bosonic modes of the environment that now also acquired a momentum. You can write down the interaction between the fermions and bosons in this case, and bosons look like phonons because they have momentum. And this interaction Hamiltonian is very interesting. It is different from what you would have in a typical transmon situation. Because in a transmon situation, you're in a rotating frame, and therefore you conserve the number of particles. Here, the number of particles is not conserved, and you have three possible processes. One process is a fermion-boson scattering, when you basically take a fermion with one momentum, you change it in another, and you emit or absorb the boson. Another process is a boson-fermion-boson generation. What happens, out of the vacuum, you generate two fermions, and you absorb the boson. And then there is a third process, inverse. It's a two-fermion annihilation. It's when you have two fermions, they approach each other on a sufficiently small distance, so their wave functions overlap, and there is a process of their annihilation. And those three processes work in a different way. First of all, you can compute the transition rates for those processes, and they will depend on this Bogoliubov angle, meaning they are sensitive to where you are relative to the critical point. You can compute transition rates for the scattering and also for recombination and generation. And what is really important, that in the vicinity of the critical point, the fermions have a typical energy corresponding to the temperature. So their momentums are actually relatively fast, because temperature, the thermal momentums in this system, are much, much bigger than any typical momentums corresponding to the rates that happens with the spatial inhomogeneity or a scattering rates. Those are proportional to the coupling to environment. Thermal momentums are fast. So if you do that, then you can convince yourself that as you pass through the critical point trying to maintain a quasi-equilibrium, you can actually be successful with that. And you can do it relatively fast. The trouble happens, in fact, as you move into the semi-classical region, where the gap, this value of the gap, is actually bigger than the temperature. This is where the problem occurs, is right there. And in fact, what happens in this region is something fairly simple at the beginning. You have effective mass. H fermion, because you have a parabolic band, has effective mass, and that effective mass actually grows as you move away from the critical point. And the first obvious observation is that as your gap grows from the ground state, from no fermionic state, as you move away from the critical point, it becomes harder and harder to generate fermions. So the equilibrium concentration of fermions as you move through that point is getting depleted. So there will be fewer and fewer fermions there. And that has a consequence, because for fermions to annihilate, they have to come close to each other. So basically, if you have annihilation process, it will be proportional to the product of the concentration. It's quadratic in the concentration of fermions, because the recombination requires 2 fermions, so it's quadratic. But if the concentration of fermions goes down, so will be recombination process. That means that in that area, and people in semiconductor physics know this very well, the intra-band processes, the scattering within the fermions from each other, the scattering of fermion on a boson and changing its momentum, are very fast, much faster than the process of recombination and generation. And you can actually solve that equations for the fermion scattering and obtain the momentum relaxation. And the momentum relaxation is a very fast process. In fact, it accelerates with time as the fermion mass increases. Now, because of that, it is possible to separate. You can actually assume that fermions scatter its momentum so fast that essentially you create a distribution that you can be interested in one number, which is the number of fermions in a band. And then if you do that, then you have a very simple equation. You don't really care how this fermion moves in space. They move fairly fast. So you just have a number, a total number of fermions, and then what you do, you can write a simple equation. Well, you have to write it through some mathematical manipulation with a quantum kinetic equation of that. I'm just giving you an answer. It's a simple equation of the bimolecular reaction where the concentration of fermions is decreasing with the recombination rate and is proportional to the square of that concentration itself. So when you can analyze these dynamics, it's a very different dynamics from the equilibrium one, because the system becomes substantially non-equilibrium. What happens, however, because as you keep recombining those fermions, the distance between fermions become large. And when the distance between fermions become larger and larger, these fermions become having a hard time reaching each other. What also happens in this situation, because if you look microscopically, how actually a fermion moves, it's a very archetypical, simple picture described, I think, in 1946 by Chandrasekhar. Because you have a particle whose momentum undergoes Brownian motion. And as a result, the coordinate of the particle undergoes diffusive motion. So it's a simple diffusive coefficient that you can describe. So these fermions, they're like a classical particles, but the coefficient of diffusion knows about quantum mechanics, because the motion of the fermion is really, remember, the fermion is a glorified king. It's a domain wall. It's not exactly a domain wall, but it's nice to think of that. But that domain wall has a width, which is proportional to the mean free path. It's a coherent length. So in a way, a large groups of spins get reconfigured and as the fermion moves. So it's a multi-spin collective motion. So for this diffusion coefficient has a quantum origin. And in fact, it's really getting larger and larger as you approach critical point, and vice versa, it becomes small. But as you go away from the critical point, your diffusion coefficient becomes smaller and smaller. And the fermions now have a problem to reach each other. If they have a problem to reach each other, they cannot recombine. And a very simple illustration of that, and then once that happens, the system goes in a strongly non-equilibrium, highly correlated regime. And it's again known in chemistry. But I would like to emphasize this simple picture describes what is going on in a simple example. So what happens, suppose I'm sitting in one of these blue dots, and I'm trying, it's my fermion, and I'm trying to reach another fermion. Two things happen at the same time. On one hand, fermions in average recombine, so their concentration decreases. And in fact, because it's a bimolecular equation, the concentration tends to decrease inversely proportional in time. That means the distance between fermions in average grows linearly in time. However, the fermion tries to diffuse. And as we know, if I compute how much distance it travels over the time t, it's a square root. So the square root at the beginning wins, but eventually loses the linear distance. And when it loses, then the fermions no longer have time to approach each other. And the situation is essentially scale-free. Because what happens, whenever they were close to each other, they recombine with each other and they create a hole. So the whole system creates a hierarchy of these holes. And you can analyze this, but the bottom line, that the process of recombination, the process of annealing, slows down significantly at that point. And you can just take the concentration, the crossover concentration, when this happened, and you can assume this is where your solution for quantum annealing is. And you can analyze, and in fact, that crossover concentration is a non-monotonic function of quantum annealing rate. And in fact, the optimum is fairly close to critical point. It's still far away. You're in a semi-classical region, but it's inversely proportional to the temperature. So it's fairly close. The net result I would like to emphasize is here. And unfortunately, there is a blog with my name that I don't need here, because it really prohibits me to show. Hi, let me do this. Oh, wait a minute. What happened? OK. So what we did is a very simple comparison, just to give you a main message. If I would be moving with no coupling to environment at all, we would have a Kimbo Zurich. We would have, as I promised before, the number of excitations you create, which is a square root of velocity. What we're going to do now, we're going to play this game. Let's remember that number of excitations, OK? And let's actually consider what would be a rate of noise-driven, this non-equilibrium diffusion quantum annealing to reach the same density of defects. And now we're going to paint a ratio of this rate, optimal rate of quantum annealing that terminates at crossover point, divided by Kimbo Zurich rate to reach the same density of defects. And in fact, that ratio, beta, is an inverse temperature. It's extremely large. Beta is very large. Alpha, it's coupling to environment. It's very small. And there is a logarithm sitting there. So what is important? The lower is the temperature, and the smaller is the coupling to environment, the more the mechanism driven by the quantum diffusion mediated by environment become faster than the Kimbo Zurich mechanism. This is an interesting finding, that you can actually find an approximate solution better with environment than without it. But we did use this specific coupling to environment, which is a Glauber process. Anyway, I'm finished, and I think.
Question?
So I have a question about this condensed matter point of view of quantum annealing. So to talk about Gilbert-Zurich and scalings and divergences and things like this, the thermodynamic limit has to be well defined. And I noticed, I think this goes back to the very first works by Anatoly, that the way this is done is that the JIJs have to be scaled with square root of n, no? Otherwise, the energy density in the thermodynamic limit.
Your n has to be large enough.
Yes.
And it's
and you have to scale the j's with square root of n.
Square what?
The j's, the interactions in the spin glass, the JIJs.
In this problem, you don't need to scale j with n. It's 1D. In this problem, you don't need at all.
Okay.
There is a very simple thing. Your gap.
So this is only valid for 1D that we heard.
you can generalize it to 2D, and this notion of the diffusion-limited regime will still be there. In 3D, it will be more generic. Diffusion would always win. We can talk about this separately. But the bottom line is this. At the critical point, your gap scales inversely as a polynomial of n. As long as your temperature is much bigger than that, then as you go through the critical point, the motion is essentially macroscopic because you involve a lot of levels. So that description becomes correct. Yes. As long as you have a lot of levels under your temperature.
Okay, let's thank Vadim once more.